Alright, so does everybody have access to HY8 this morning? Either on your laptop or on the desktop there? I think the desktops have version 7.5, but it's largely similar to 7.6. We don't have class on Monday, but we will have class on Wednesday, of course, and that's the day your homework assignment is due. And so, unfortunately, we're not going to see each other again between now and then. But if you have any questions as you're working through either the flume calculations or working on HY8, you can send me an email and I'll do my best to respond to that. Alright, so we're going to pick up where we left off, and last time we were looking at this top view of a stream that's crossed by a road, and the width of the stream is 5 meters. It's a rectangular channel, and what we want to do is analyze what's going to happen when 25 cubic meters per second is our design flow, going up to a maximum flow of 30 cubic meters per second, and just take a look at essentially how high is the headwater getting and whether this 24-inch diameter culvert is going to be sufficient to carry the design flow. So where we left off last time, we didn't get far. We first of all need to close this and make sure that you are in SI units before you add the crossing. And so switch to SI units, and then here do culvert, new culvert crossing. Now remember, this first example, it's okay if you just watch rather than follow along, because we've got two other examples that you can get the practice with. So if you just want to watch on this first one, then that's okay. And we verified that the units are SI by the column that has CMS, which is cubic meters per second. Okay, so from the problem statement, we know that the design flow is 25 cubic meters per second and the maximum flow is 30. One other thing I'll mention is that right now by default the minimum flow rate it's going to analyze as 0 cubic meters per second, but you can take that up to a higher flow rate, and the reason for that is it's like zooming in on a graph. So you know how if you're using Excel and you're trying to take a look at a trend, if you have it go from 0 to some big number, you may not be able to zoom in on a certain part of the graph that you're more interested in. Like if there's a spike in the data, you may have to zoom in to be able to see really the details of that spike. And the same thing is true here. If there's something really interesting happening at a flow between 20 and 30, then you could change the minimum flow rate to get a better idea, more resolution on what's happening in that intermediate zone, rather than from all the way to 0 up to 30. Because as you're going to see, it provides a table that has maybe around 10 rows or something, and it's telling you the depth for each of those different flow rates. And so you'd get more of the rows in the vicinity of the flow rate you're interested in if you changed it. So I'll show you that when we get to it. The bottom width of the channel is 5 meters. It's rectangular, remember. The longitudinal slope of the channel, 0.0025. So this is the slope of the channel downstream of the culvert. So the tailwater is what's after the culvert. Manning's N, if I remember correctly, was 0.05 is the roughness coefficient of that. And then the channel begins at an elevation of 299.95. That's the elevation of the channel that matches up with the downstream end of the culvert. 299.95. Okay, now it wants to know about the roadway. And the reason why is that the water level, here it's depicted in blue, it could get higher and higher and higher, and eventually it's going to flow over the top of the road. So it needs to know what's the elevation of the road. Alright, so it needs to know not only what's the elevation, but also like what's the width of the road. Because here in the top view, think about if the water level keeps going higher and higher. So here it's going to flow over the top as though it's a broad crested weir, and it wants to know like what's the length of that weir. So if it's flowing over the top, how much contact area is there between the water and the roadway? All right, so let's see, the crest length is 5 meters. That's the same as the channel width in this instance. The elevation of the road, 307 meters is the elevation. All right, it's paved, and now the top width is talking about the parameter, how long is it from the left edge to the right edge. In other words, we've got 2 lanes we can see, but it wants to know, like if the water's flowing over the top of that, how much contact area is there. And so the top width of the road we can get from this, where it was saying inlet station 1 plus 0, 0, outlet station 1 plus 2, 0. It looks like the paved section is most of that culvert length. So let's just say that it's 20 meters in width. Now the flow conditions aren't very sensitive to this width, but it's still good to have it as accurate as possible. I don't think that entering this roadway station makes any difference in the calculations, but I mean, if we need to come back to it, then we can add that in. But I don't think that that roadway station really ends up doing anything. All right, now the culvert. So this is the pipe that's going under the road. So we told it about the channel downstream. We told it about the road. And now this is the pipe that goes under the road, connecting the headwater, which is the flow upstream of the crossing, to the tailwater, which is the flow downstream of the crossing. So it's a circular concrete culvert. The diameter is 610 millimeters. That's what you get if you convert 24 inches to millimeters. Embedment depth is talking about, it's a little bit having to do with, remember the pictures I showed you of whether the pipe protrudes from the front of the culvert. It has to do with that, and so we're not going to change the embedment depth, but in the homework assignment you're asked to do a design where you could play around with things like the embedment depth, whether the culvert has a head wall, and so on. We're going to leave embedment depth to 0. It's a straight culvert, meaning that the pipe goes directly through it, and it's not at an angle. If it was at an angle, its capacity would be changed. So it's straight. Inlet configuration, square edge with head wall. Now, by the way, these question marks, if you click on it, will take you to the user manual, and it has different pictures of these options. And so you could look at, if you've forgotten what mitered looks like, that's where it's at the angle with the slope, or if it's just square and does have a head wall. Let's see if this is finished auto-saving. It'll let me come back to some of the images from before. Yeah, all right, so this is mitered, for instance. This has a head wall because it's like a concrete slab that surrounds the opening of the pipe, or if it's just projecting straight out. So let's just say, for instance, that it has that square edge with a head wall and there's no inlet depression, meaning like a sill upstream to collect sediment. These are all, these three, inlet configuration, inlet depression, they're pretty minor. They don't have huge effects on the flow capacity. But what we do have to do, we have to specify how long the culvert is. And so we're going to do that with the station. Back to the example slide that gives us the details about how long the culvert is. From this view, we can see inlet station is 100, outlet station is 120. And it's from that that it gets the culvert's length. So 100 meters, outlet station 120. Now the inlet elevation, we look at the invert here, and it was at 300. The outlet is at 299.95. And so the elevation of the pipe and the elevation of the channel matches up at the outlet. So 300 and 299.95. We didn't tell it the slope of the culvert, but it will calculate the slope of the culvert with the length and the elevations that we've just entered into these fields. Jeffrey, do you have a question?
I've already asked the number of barrels. Is that the number of openings underneath the roadway?
Yeah, it's how many pipes. So right now we just say it's a single 610 millimeter pipe, but we could put in two 600 millimeter pipes, 610 millimeter pipes by just changing that.
Okay.
All right. All right, so let's click Analyze Crossing. And what this does is tells you when the water is at a certain elevation, how much flow is going through both the channel and how much is going over the top of the roadway. So what we see is that overtopping occurs, meaning that the water, well, if we look at the side view, overtopping is when the water gets to 307. So the water depth got to 307, and now some of the flow is going over the road instead of all of it going through the barrel. So when we clicked Analyze, we got our answer pretty quickly. Is this 610 millimeter pipe going to be big enough to convey 25 cubic meters per second? So look at what happens at 25 cubic meters per second. So at 25 cubic meters per second going through the channel, only 2 is going through the pipe, and 23 is going over the top of the road. So this pipe is wildly undersized. If we had any hopes of trying to get 25 cubic meters per second through that pipe, we are now sorely disappointed. It's not going to work. All right. So there's a couple of different ways for us to explain that. We could say at 25 cubic meters per second, only 2 is going through the pipe and 23 is overtopping. The other way to look at it, let's see, how do I get that report back up? Analyze crossing. All right. So the other way of explaining it is that before overtopping occurs, like just when that water level has gotten exactly to 307, 2.02 is going through the pipe, and so the clear answer is it's not going to be working for us. Now, this is that same cross-sectional side view, and it shows the elevation of the water at the design discharge of 25 cubic meters per second upstream and the depth downstream. So the analysis that we've performed, the question was, is this pipe okay? The answer is no. Now, it may be the pipe's fault. It may be that the channel itself is just not adequate, the downstream channel. And so let's just play around with our data a little bit. If you double click in the left panel here in the Project Explorer, it'll bring up the Culvert parameters again. And so what if we increase the number of barrels to 2? Are we going to get more capacity, less overtopping? You know, we only 23 cubic meters per second was going over the road. That's a lot of water. It's going to cause some serious damage. It could scour away that paved surface as the water goes down off the top and re-enters the channel. There's going to be a lot of turbulence and scour energy there as well. So maybe 2 barrels would be okay. So we analyze the crossing, it gives us an updated table, and well, it is a little bit better. Now at our design flow of 25, nearly 4 cubic meters per second is going through the 2 pipes, but still 21 cubic meters per second of roadway discharge. So the cool thing about this is we can iterate really quickly. We can say, well, what if we switch to a 1500 millimeter pipe? It's a 1.5 millimeter diameter. That's now getting pretty big. And we've got 2 of these barrels. Analyze the crossing. All right. Now, overtopping occurs at 22.5 cubic meters per second. So we're getting good and close. You know, there's just a little bit of overtopping at our design flow of 25 cubic meters per second. Let's zoom in and look. Instead of starting at 0, let's see if we go from 20 as our starting point, and now maybe 1600 millimeter. Now I don't know if we could find a 1600 millimeter commercially available pipe, but we're just kind of optimizing here to see what the situation is. So we've got 2 1600 millimeter circular concrete pipes and analyze crossing. So now the table that comes up, you'll notice that it starts at 20 cubic meters per second. And so that gives us a little bit of a finer resolution in exactly what elevations are corresponding to which flow rates. And so instead of starting at 0, now it's giving us in increments of 1, 2, 3, 4 cubic meters per second. So it's every single cubic meter per second. And so when does the overtopping occur? We're only getting 0.1 cubic meters per second of overtopping at our design flow. And so sometimes what we'd have to do is go back to the client and say, you know how you were asking if that single 24-inch pipe would work? Boy, it's not going to work at all. It's going to have to be so much bigger than that. It's going to have to be, you know, like in terms of cross-sectional area, like almost 10 times larger than what you asked me. And so, are you sure 25 cubic meters per second? That seems like a lot of flow. You know, like revisit the hydrology that gave you that design flow. You know, like maybe it was based on a really poor model. Maybe it was based on the rational method and a high runoff value, and it was just kind of a poor estimate of what the design flow rate might be. Or maybe it's a good estimate of the flow rate and you just need a much larger pipe than originally anticipated. All right, so that's how we can use HY8 for a really simple, quick analysis. Let's consider this second example. Okay, so this is the side view. This time, instead of being circular, this is a box culvert. And so you can see that it is rectangular with 1.5 meter width, 1.5 meter height. Its N value, talking about the material that the culvert is made out of, is 0.013. And that's a Manning's N value that corresponds to concrete. So in the material properties, when we set it up, we're going to say it's a concrete box culvert. Now, in this sketch, the first example, I told you the elevations. But in this case, we don't know necessarily like what's the mean elevation above sea level, but we know the slope of the culvert. And also that slope of the channel is presumed to match the slope of the culvert. And so we're going to have to come up with our own elevations and then calculate the upstream and the downstream, the downstream elevation based on the slope. So let's just say, for instance, if this invert elevation is 100 meters, we're going to have to calculate the downstream invert elevation based on a length of 40 meters and this slope. And then the downstream channel roughness is 0.05. Now there's two things that we're going to look at here. We're going to analyze with this culvert, then how much of a flow rate causes the headwater to get up to 2 meters. So we're kind of like stress testing this culvert to find out, you know, if we have this is actually in place somewhere and we're a little bit worried about the water getting 2 meters deep. We want to find out what flow rate would cause the headwater depth to be 2 meters, and then the channel width downstream is 5 meters. And I think that this one is also a rectangular channel downstream. Oh wait, hold on. Channel width is 5. Okay, and then in part B, we're going to change the downstream channel to some different value besides 5 that will affect the tailwater. All right, so two different analyses here. Let's set it up together. We need to start from scratch here. We'll delete our existing model here. So File, Close. Well, you can save that if you like. There's so many different reports you can look at. But that analysis table will usually give us what we need to answer the questions. Does everybody here know how to take a screenshot? There's a button on your keyboard that says Print Screen. I think I had you do screenshots in the fluid mechanics lab. Right. So in the homework assignment, I'm asking you to prove that you've done an analysis. And so what you need to do for those screenshots in the homework assignment is take a screenshot of this. This is the input to the model. So print screen, you start up Word and paste the screenshot into Microsoft Word. Just as a quick revisiting here. All right, and then I'm going to crop out the part that's irrelevant so that it can zoom in on what is important. These side areas here aren't helping to address what was in the input. Okay, so since I've cropped that now, I can expand that and it's easier to see. So that's the input, and then the output, analyze crossing, it's this table. So print screen, and then this proves that you did the analysis and it's the basis for the explanation that you provide. Like, for example, if it is asking, how big does the culvert need to be, this is where you could show, well, the input I gave you yields this output, and it shows that those two 1.6 meter diameter circular concrete pipes only yield a tiny bit of overtopping at our design flow. So that's just, in essence, how to do the screenshots and submit what you've done in HY8. All right, so close this one. We don't want to save it, and we're going to do a new crossing. This again is also SI unit, so once again we have to specify SI, and then culvert, new culvert crossing. All right, so interpreting this sketch, starting up in the upper left here, what flow rates, well, what does the problem say? What flow rates? It doesn't even specify. We don't know. So we just have to put in some flow rates and then see how high does that take the headwater. So let's just say 10, from 0 to 10. And we can put the design and maximum as the same thing. All right, the tailwater is rectangular. It's a rectangular channel downstream. And in part A, we're saying we're going to use this start value of a channel width of 5 meters. Okay, so it's a rectangular 5 meter channel. Bottom width 5. Channel slope 0.007. Okay. So channel slope 0.007. The roughness of the channel 0.05. Channel invert. Remember, what that's asking is what's the elevation here where the downstream channel matches the culvert. We haven't calculated that yet, but we can from the slope that's given. So if we assume that this elevation is 100 meters, then this elevation is going to be 100 meters minus 0.007 times the length of the culvert, which is 40 meters. All right, so how much lower than 100 is that downstream elevation? I think what we end up with is 99.72. Can someone double check? Yeah, that's right. Okay. $99.72. And while we're at it, let's go ahead and put that same stuff into the culvert. So inlet station of 0, outlet station of 40. So now with that we've defined the length of the culvert, inlet elevation 100, outlet elevation 99.72. Do you remember the picture of Colorado, the culvert where those 3 pipes were going under the road? In that picture, the invert elevation and the channel invert was the same. Like, because the water came out of the culvert and then it plunged down, and the river bottom was probably a good 4 or 5 feet deeper. But in both of these examples we've worked so far, the river matches up exactly with the bottom of the culvert invert. Okay. All right, so what else do we need to put in here? Roadway data. We don't really have an idea of how much height is there, and we're never going to get that far because we don't want to find out how much overtopping there is. We just want to find out what's going on when the headwater gets up to 2 meters. So all we have to do is we have to build the front side of that culvert so that it's at least 2 meters tall, because we want to find out what's happening hydraulically through the culvert on the way up to 2 meters. And so let's just say that the crest length, I guess it would probably be the same as the channel width, right? It said that the channel width is 5 meters. It's never going to matter because the water isn't going to overtop. You know, when the headwater is at 2, it's not yet overtopping, and so it's not going to use this weir flow data. So, I mean, I'll put these things in here, but it doesn't matter. The crest elevation has to be at least 102, so I'll just say 103. That's the only parameter that does matter, is making sure that the overtopping doesn't happen before we get to a headwater elevation of headwater depth of 2 meters. Top width, I don't know, 10 meters. Does everybody understand what I'm saying, why this doesn't matter so much? Because the question is just all about the headwater getting to 2 meters. And so we just need this height to be more than that, because we don't want to know what's happening with the overtopping. We just want to know what's the capacity of the culvert when the headwater is 2. All right, culvert isn't circular, it is now rectangular. So we'll put concrete box, and you'll notice that the span and the rise have units of millimeters. And so we're going to have to convert from the given data of meters and make it 1,500 millimeters of a span, meaning the width, 1,500 millimeters rise. Now again, the embedment depth is related to like if the culvert is embedded inside the front face of the side slopes, we'll just leave that blank. The Manning's N is talking about the roughness of the concrete, and we were told that the roughness is 0.013, which is a little bit rougher than this default value for concrete. So let's update that, 0.013. It's straight. And now the inlet configuration, you know, the angle of the wing wall can be changed. Let's just start with this default assumption of a 90-degree head wall. So the concrete is up against the face of the soil that is underneath the road, and we don't have the wing walls guiding the flow into the pipe. If we did, then the capacity would be improved a little, and we might try that. Let's look at, first we'll do the analysis with a square edge 90-degree head wall, and then we'll do the other one. We'll add one of these wing wall just to see how it changes the flow rate. All right, I think we have everything we need. We tell it how much water is going through there. We tell it the downstream conditions, how high the road is, the culvert parameters. We can click Analyze Crossing. And the question we're answering here is, what flow rate causes the headwater depth to be 2? So headwater elevation, you see 2.1. It looks like the discharge is 6. So if I want to know exactly what is the discharge when the headwater elevation is 2, I'm going to have to do that thing where I zoom in on the flow. So what I really want to do is I want to look at what's happening between 5 cubic meters per second and 6, because right now I don't know exactly what flow rate it is that causes the headwater elevation of 2. I just know that it's between 5 and 6 cubic meters per second, because this is below 2 and that's slightly above it. So let me close this and double click on the culvert. Let's make it from a minimum flow of 5 and the design and maximum flow of 6. Analyze that crossing again, and we have it going in much smaller increments, and here we have 2.01. That's pretty close to 2. And so what I can now say in words, I'm going to write this on the board, like the interpretation of our analysis here. When the headwater depth is 2 meters, the flow capacity through the culvert is 5.70 cubic meters per second. Now let's just double check in the problem statement and make sure that we've addressed what it's asking. So, what flow rate would cause the headwater depth to be 2 when the downstream channel width is 5 meters? Yes, I think that what this is saying is for the downstream channel being rectangular and 5 meters wide, then the flow rate through that culvert will be 5.7 when the headwater elevation is 2.01. And that's close enough to 2 that, I mean, if we wanted, we could say, well, let's reanalyze the culvert between 5.6 and 5.7 cubic meters per second. And I suppose we could get that elevation nailed a little bit better, but I mean, 1/100th of a meter is pretty close.
So what number did you change on the last data?
What I changed was the minimum and the design flow rates to zoom in, you know, like, because before when I was going from 0 to 10, the problem with that was that the table doesn't, I don't know exactly what's going on at the headwater depth of 2. I know what the flow rate is when the headwater depth is 1.8, and I know what is the flow rate that corresponds to a headwater depth of 2.1. I guess I could do my own linear interpolation, but it's actually, I mean, the behavior isn't exactly linear, so it's better just to zoom in by changing that to 5 and that to 6, reanalyze the crossing. Yeah, so depth 2, flow rate 5.7. And no overtopping. By the way, like, what if we made a mistake? Remember how I just had to, like, pick an elevation for the roadway? Let's see, where did I do that? Yeah, crest elevation. What if I said 101.5? I've accidentally put the elevation of the road too low. Now I'm going to have a bunch of overtopping flow, and I can never find out what's going on with the headwater. You know, the headwater never gets to a depth of 2 because the road is lower than that. So that's why I kind of just had to make sure that the roadway elevation was at least as high as 102. Even if I did 102.2, I think that'll probably be high enough to where all of the flow is going to go through the pipe and none of it is going to be overtopping. So what do you think? Do you like HY8 so far?
It's not that bad.
Not that bad. In comparison to what?
I can't remember. I like water gems. That's a little confusing.
You like water gems?
Yeah.
All right.
It's just a matter of making sure you plug in the right numbers in the right spot.
Yep, that's what it is. All right, so let's do the part B. Part B was asking, all right, so find the rectangular channel width that will cause the tailwater depth to be 2 for the flow rate found in part A. Oh, that's so confusing. What does that mean? All right. So part B is saying, all right, for Q equals 5.70 cubic meters per second, how wide does the channel have to be for, okay, so B equals what for depth equals 2 meters? So what we're actually analyzing in part B is the downstream channel. And this is something I pointed out on Wednesday, but I'll show you again, this button where you can view the rating curve. So that rating curve tells you the relationship between flow rate and water depth. So what we're looking for in part B is we want to find out, all right, if we want the water depth to be 2 meters for the flow rate of 5.7, how wide does the channel need to be? So we're kind of like designing that downstream channel. Okay, so so far, the depth, oh, this is zoomed in between 5 and 6. And so here's the 5.7. So 5.7, the water depth is only 0.898. So should we make the channel wider or narrower to increase the depth? We're saying we can tolerate a depth downstream of 2 meters. Right now, with as wide as the channel is, the depth is only less than 1. Let's make the channel narrower. So would a 4-meter wide channel be okay? What we're trying to do here is try and save the client money, because excavating a 5-meter wide channel is very expensive. Maybe, based on our tolerance for 2 meters of depth, maybe a 4-meter channel would be okay. So I change the bottom width to 4. I view the rating curve again. All right, so 5.7 flow. Now the depth is up to 1.08. I can make that channel a little bit narrower, 3. All right, 5.7 flow, depth 1.4. Oh, we're getting closer.
Don't go to 2. You'll
Don't go to 2.
It passes.
Between 2 and 3? All right, so let's try 2.5. 1.7. All right, we're getting closer. I think I can go narrower than 2.5, 2.35. This is like the Price is Right in a way. All right, you want to get as low as possible without going over the depth. So you get the idea, right? This is iteration. And by the way, doing these calculations by hand, that'd be brutal, because you're solving Manning's equation for a bunch of different flow rates. You're solving the depth. And so it'd be like an iteration within an iteration. So, this is an optimization thing where you're finding how narrow can the channel be and still have a depth that isn't too much.
As close as I can get it, it looks like around 2.2.
2.2? All right, let's try that. 2.2. 5.7. Yeah, that is pretty tight. 2.16? Let's save some more money. 2.16. Now that is perfection. Well done, guys. You nailed it. It's like a dunk. All right, so I'm going to stop talking because I want you to try Culvert example 3 on your own. So I've got the problem statement here on the screen. You're going to do design, which is that iteration we've just been talking about, where you change things over and over again until it's good enough. Now this is a little bit different because we want the maximum headwater to be 7 meters when we're carrying 10 cubic meters per second. The channel is trapezoidal. The bottom width is 3. We have the roughness. 1-to-1 side slopes on that trapezoid. So part A is design a culvert so there's no overtopping. Part B is we can have 0.1 cubic meters per second of the 10. Excuse me, we can have 1 of the 10 go overtopping. No elevations are given, so you will have to assume one and calculate the other. All right.
So what are the limits of this program?
What do you mean?
Like, is there any limitations to it, or?
Oh, there must be, right? It only designs culverts?
Does it account for like the
We've got that same 99 point. All right, we're almost out of time, so your design may look different from mine, and that's okay. When we're doing design, we can all get different answers. When we're doing analysis, we should all get the same answer. But this is saying design a culvert so the maximum headwater is 7 meters. So I just put in 1,000 millimeters, and it looks like the headwater gets up to 7 when only 5 is getting through the pipe. So I need to make my pipe bigger because I get to headwater 7 before I achieve 10 cubic meters per second through there. So now it's the optimization game where I'm playing around with the diameter. Would 1250 be big enough? So now I achieve 8 cubic meters per second before overtopping occurs. So still not quite big enough. Let me close that and optimize a little bit more. What about 1400? And analyze crossing. Now that's big enough. It is big enough because when the headwater gets up to 7 meters, then I can get 10 through there. So I could make it a little bit smaller, but 1400 is a nice round number. So let me just say that my answer to the first part is the culvert has been designed so that so the headwater depth is 7 when 10 is getting through the pipe. Now B is a little more relaxed. It's saying, well, 1 of the 10 can overtop. So now that means my pipe can be a little bit smaller. And so if we have, a rugged paved top, then we could maybe see what happens at 1,300 millimeters, analyze the crossing. So at 1,300, yeah, it looks like at a depth of 7, 9 is going through the pipe, which means, I wonder where the roadway. So it's getting a little high. So I'd need to optimize that a little bit further. But I think you get the idea that, the water can go one of two places. It can go either over the top of the roadway or it can go through the pipes. So on the homework assignment, you get some more opportunities to play around with HY8, and the tricky thing, as always, is interpreting the geometry and kind of trying to understand the problem statement. And so hopefully these examples gave you an initial exposure. And remember, the assignment is due before class on Wednesday. So I won't be here on Monday, but I will be checking my email over the course of the weekend, and I'll be in the office on Tuesday. If you needed to pop in then, I'd be glad to see you.
Can you pull your crossing data up?
Mm-hmm.
I don't know where we're trying to get it to where you